In this chapter, we're going to begin to take a look at probability. And of course, to start out, you really need to understand some of the fundamentals of probability. A lot of the work that has been done on probability has been done to support various gambling ventures starting out in Las Vegas. The idea there, of course, is to make the probability work in the favor of the house. So if you play long enough, they're going to win, but also seem attractive enough to those individuals who are playing to think that they have a chance of coming out as a winner when they're playing the various games in probability. When we look at this, we're going to look at experiments, counting rules, and how probabilities are assigned. We're going to look at a number of events and what their probabilities are, some basic probability relationships, and some conditional probabilities. From a definition point of view, when we talk about things, we say that outcomes are the most basic possible results of observation or experiments. An event consists of one or more outcomes that share a property of interest. The probability of an event expressed as P, parentheses event, is always between 0 and 1 inclusive. One of the things that you need to remember from this course, and not a whole hell of a lot, is that probability always is a number between 0 and 1. A probability of 0 means the event is impossible, and a probability of 1 means the event is certain. You can't solve a problem in probability and get a number bigger than 1. It's not possible. If you do that, you've made a mistake. Okay, so if you take a look at the simple bar on the right-hand side, you can see that a probability of 1 says that something is certain, and a probability of 0 is it's impossible. If today were Sunday, we could say that the probability that tomorrow is Monday is 1 or 100%. We could also say that the probability that tomorrow is Thursday is 0. It's impossible. Beyond those couple of simple things, most cases, not all, but most cases are a number between 0 and 1, but very few are impossible or certain. So the theoretical method for equal or likely outcomes, you could look at in steps. You would count the number of total possible outcomes, and among all of the possible outcomes, count the number of ways the event of interest A can occur. And the formula is simple. The number of ways that A can occur divided by the number of possible outcomes. And so here now is an example. Assuming an equal chance of having a boy or girl at birth, what's the probability of having 2 girls and 2 boys in a family of 4? And what you can see listed below are all of the possibilities in that scenario. You could have all 4 girls. You could have girl, 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 boy, girl, girl, boy, girl, and so on, down the whole list. There's 16 possible outcomes. 6 have the event of 2 girls and 2 boys. So, following that simple formula, the number of ways it can be 2 boys and 2 girls is 6 out of a possible 16. So you would create a fraction, 6 over 16, reduce it to a decimal, 6 divided by 16, and you could say that the outcome of having 2 girls and 2 boys is almost 36%, 0.357. If the probability of an event A is the probability of A, then the probability that the event A does not occur would be 1 minus probability of A. It sounds complicated, but it's not. Since the probability of a family of 4 children having 2 girls and 2 boys is 0.375, the probability of a family of 4 children not having 2 girls and 2 boys is 1 minus 0.0375 or 0.625. So, following the formula that we had, we would list all the possible outcomes. We would use the table or a figure if it was helpful. We would identify outcomes that represent the same event and determine the probability of each event. And then we would make a table listing each event and the probability. Here is all of the possible outcomes when a pair of dice are rolled, as shown below. And you can see that every time you roll a pair of dice, you're going to get a number between 2 and 12. Looking at the table on the bottom, there's only one way you can get a 2 and one way you can get a 12 out of the 36 possibilities. But you can go all the way across and you'll be able to figure the probability of rolling any number between 2 and 12. 2 events are dependent if the outcome of one affects the probability of the other event. The probability that dependent events A and B occur together would be the probability of A and B equals the probability of A times the probability of B given that A has occurred, where the probability of B given A is the probability of event B given the occurrence of event A. Now this stuff sounds complicated. The fact of the matter is when we get into the examples of how you do it, it's really pretty simple stuff. And you can extend this principle to any number of dependent events. Either probabilities are overlapping or non-overlapping. 2 events are non-overlapping if they cannot occur together, like the outcome of a coin toss, as shown in the picture to the right. You can toss a coin and get heads, you can toss a coin and get tails. You can't get both. For non-overlapping events A and B, the probability of either A or B occurs as shown below. The probability of A, in this case, heads, plus the probability of B equals the probability of A or B. Again, sounds complicated. When you flip a coin, the probability of getting heads is 50-50. So it's 1 over 2. The probability of getting tails is 1 over 2. If you add 1 over 2 and 1 over 2, what do you get? 1. Because all of the possible probabilities have to add up to 1 or 100%. 2 events are not overlapping if they cannot occur together, like the outcome of a coin toss as we looked at to the right. For non-overlapping events A and B, the probability of either A or B occurs as shown below. Probability of A or B equals the probability of A plus the probability of B. There is a formula also called the at least once rule for independent events. Suppose the probability of an event A occurring in one trial is probability of A. If all of the trials are independent, the probability that A occurs at least once in n trials is shown below. So the probability, the formula is the probability that at least one event occurs in n trials equals 1 minus the probability that A doesn't occur in n trials. And so if you simplify that formula, it's 1 minus the probability that not A raised to the nth power. It only works when probability is a constant. Like flipping a coin, it's always 1 out of 2. Rolling one die, getting a number is always 1 out of 6. We'll look at some examples of this later on in this chapter. Okay, the probability for overlapping events is a little different. Two events are overlapping if they can occur together, like the outcome of picking a queen or a club, as shown to the right. For overlapping events, A and B, the probability that A or B occurs is shown below. Let's take a look at that. The probability of A or B is equal to the probability that A occurs. So the probability that a queen is picked is 4 out of 52. The probability that a club is picked is 13 out of 52. But if you look at the picture above, you'll see that the queen of clubs is overlapping. We can't count it twice. If we count it as 4 out of 52 for the first, and we don't do anything for the second, we say there's 13 out of 52, we would be wrong. Because what we need to do is we need to subtract that queen of clubs. We've already counted it. So that's why the formula would be probability of A plus the probability of B minus the probability that A and B, which represents the queen of clubs. This principle can be extended to any number of overlapping events. So this is going to conclude the first section of slides for this chapter 4. We'll pick it up again in the second group.